Welcome to the start of Lecture 3. So today we'll actually get into some applied use of Matlab. We'll look at linear algebra. Of course, that was one of the topics that we ended up with in the course. And so we'll look at using Matlab to solve linear algebra problems. We'll also look at how Matlab is used to represent polynomials. One of the things we'll get into is actually curve fitting to data, and as a special case we'll see that MATLAB's able to find the regression line through a set of data. Then we'll look at some optimization techniques, although we'll primarily look at finding the zeros of an equation and the roots of an equation. And then we'll look at differentiation and integration in MATLAB, and then also how to solve differential equations. Each of these are relatively short lectures. So Octave MATLAB is great at solving systems of linear equations. So, if you look at the top of the slide here, we've got a system of linear equations in the unknowns x, y, and z. In the way we represent that equation in matrix form, of course, is we form a matrix A of the coefficients. So the coefficients here of the first equation would be 1, plus 2, and minus 3. That forms the first row of our coefficient matrix. And in the second equation, the coefficients are minus 3, minus 1, and 1. And then the last row the coefficients in the last row corresponding to the coefficients of the third equation are plus 1, minus 1, and 1. So we type that directly into our A matrix. Our B vector has to be a column vector, and it's the right-hand side here, and it's a column vector with elements 5, minus 8, and 0 taken right from the right-hand side. Now, MATLAB actually has a special notation for taking an inverse. It looks like kind of the way we would normally solve this is left multiply both sides by A inverse. So x is equal to A inverse B. Okay. Alternative MATLAB notation is A backslash B. This kind of looks like A is divided into B, right? So this is equivalent to the inverse of A times B. And as a matter of fact, MATLAB actually does something a little different, if the system is actually overdetermined. But if the coefficient matrix is a full rank and is invertible, this is equivalent to the inverse of A times B. And you can use that operation instead. As a matter of fact, kind of for us, I would encourage you to do that because the slash operator does something a little different, a little bit different than the inverse. If when A is not invertible, it'll still come up with a best solution. A regular slash, a forward slash that we think of as a regular division sign is right multiplication. So we could have like another vector forward slash, a matrix that would correspond to that vector being multiplied by the inverse of that matrix. Again, as long as the matrix is invertible, they're equivalent. Actually, I think I typed this into this slides here into MATLAB. I'm starting out the script with just the clear command to clear the entire variable space, and then this is going to clear the command window. Here's the A matrix, here's the B matrix, and here is that notation of inverse of A times B. Again, remember this is not this is really B left divided by A, or that would be left multiplied by A inverse. And then I also can compute the solution differently. And again, this is the method I'm going to recommend. We're only going to deal with actually full rank matrices here. And so when I run this, x1 and x2 should be identical. Okay, so I ran it. Let's look at the results. And we see that x1 and x2 are indeed identical. Have a bunch of other functions that are useful. You know, we looked at all of these in our linear algebra portion of our course, where we have, you know, matrix. We can compute the matrix, the rank of the matrix, the determine, and find its inverse. And I think I've got type those same equations here, same matrix. I put in here another function. There's a function to compute the reduced row echelon form of a matrix. Of course, we did that a lot throughout the linear algebra portion of the course. And then compute the rank, again, which would be a number here. Matrix is a 3 by 3, so the rank is going to be less than or equal to 3. If it's full rank, since it's a square matrix, if it's a full rank, it is invertible. Again, sometimes if a matrix is not invertible, you'll get an error when you compute the inverse when you try to compute the inverse of the matrix. Again, an invertible matrix has a non-zero determinant. So if this matrix is invertible, you know, its reduced row echelon form should be the identity matrix. It should have a rank of 3. It should have a non-zero determinant, and of course we should be able to compute the inverse. And so when I run that, you know, here's the reduced row echelon form. It reduces to identity matrix, has a full rank, has a determinant of -4. And then this is actually the inverse of the matrix. And so certainly if I take mat times E, I should get the identity matrix. Similarly, E times mat will give me the identity matrix. Sometimes you'll see a little minus sign and pop up here in front of a 0. You know, if I this is, you know, this is due to some numerical round off error in computing the inverse and the corresponding product. You know, if I actually looked at the more significant digits, by default, only what 6 points after the decimal are displayed here. If I looked at this element in some more detail, I'd see it actually has a really small part, but a really small negative part. And again, that's due to some numerical error. We didn't really talk about some matrix decompositions. This is kind of where we left off in the course, but you know, Octave can certainly do a lot more with linear algebra than we got into in the brief look we took at linear algebra. So here's an exercise. You may want to try this. This is a square system with an invertible matrix. So you should be able to solve this one. This is, of course, an overdetermined system, so it may or may not be consistent. Again, the matrix here is going to be a 3 by 2, so it's not going to have an inverse. But again, if you try the regular Matlab solution, it will give you you know, kind of a best fit solution. And we didn't talk about that. You know, what we were concerned, you know, what we would say is that you know, if this system turned out to be consistent, it may have a solution. But in the inconsistent case, we would say it actually has no solution. Matlab tries to find a closest solution, even when the system is inconsistent. So, but and that's the result you'd get here. But we didn't get into that into the course. We did look at system 1. So okay, I'm going to stop this video for a little break. Come back and we'll look at how MATLAB deals with polynomials next.